We're going to summarize the lesson we had today, the different types of bonding that we looked at, and start with ionic bonding. So in ionic bonding, remember, we have things of different charges. And if I have a plus charge and a minus charge, this is this Coulombic attraction between these charges. Anything that has opposite charges is attracted to each other. And this thing here, kind of this, these are ionic bonds. And it's not actually, last year we learned about how, different electrons are attracted to each other. But here, it's the whole thing. This is a plus charge, this is a minus charge, and so this is kind of like this imaginary bond between these two particles. When we melt an ionic substance, we are taking this imaginary attraction and we are separating them. So it is now, we're breaking a bond. Okay, so this is, we're breaking the ionic bond. And so now my K's and Cl's are all over the place because they can move around now. And this is what's happening when you melt an ionic substance. These are really strong, so they typically have a very high melting point. When we dissolve an ionic substance, I showed in the video, we had these little water molecules, and let's say I have a water molecule here, and water molecules have a negative side and a positive side. Well, this negative side is going to get attracted to this K here, so now I have this water molecule coming in and grabs this K, or I have these positive sides on this water molecule coming in and grabbing this Cl. Okay, so this is O and this is H. They come in and they're going to pull them apart now, and dissolving an ionic substance kind of looks like this. So now we have the ions floating around, getting pulled into the water, and that's what dissolving looks like. Fracturing, if I take a hammer and slam this down here so that this shifts down by one spot, well, then this kind of forms. And what happens with ionic things is, because charges are lined up now, when I slam it down, this can break like this. And so ionic things also fracture. They are brittle. So they are brittle, which means they break very easily. And that's why we have all the nice crystals, like salt crystals are very, they're very flat planes along this crystal because of the charges that they push away, and they make clean breaks. So those are some of the properties of ionic things. They have high melting points. So high melting points. They have brittle, and they're fracturing. They dissolve in water because they have its ions and they can interact with the plus and minus charges. But if I move to something like a covalent substance, so a covalent substance is like this. Like sugar. So sugar or glucose might be something like C6H12O6, and it has all nonmetals here. So these are all nonmetals. Okay? Whereas ionic things are typically made of metals and nonmetals. So metals and nonmetals. Covalent things are usually all nonmetals. And what happens here is we have bonds that form between these substances. So the carbons, hydrogens, oxygens, they're stuck together. These bonds is a very simplified molecule. If I have something like HCl is a very simple molecule. It's got an H, it's a nonmetal, Cl is a nonmetal, and between them is a bond, which is this perfect balance of electrons and protons attracting each other. Okay, attractions, repulsions. And if I have a covalent substance, and this one here is actually a polar covalent substance. So polar means it's got charges. It's got a plus charge and a minus charge. And if I have plus and minus charges, they are attracted to each other. So last year we talked about attractions a lot. These dashed lines are my attractions, that they are stuck together. When I melt a covalent substance, I am only separating the attractions. So now the bond stays, but my attractions have now been separated, okay? Not entirely. Maybe there's still some there. So for instance, I might have this attraction here. But remember, liquids have some attractions, but not as many as a solid. Solids have lots of attractions. It's got attractions everywhere. Here, I'm going to have some attractions, but the bonds stay. So when I melt a covalent substance, you keep the bonds, but we break attractions. Okay, so melting a covalent substance, keep bonds, break attractions. Dissolving, same thing. We keep the bonds, but we now have the plus and minus ends of the water are interacting with the molecule, and they can take them and separate them out. So if I dissolve sugar in water, it stays sugar. So if this is sugar, this stays the whole molecule. I just have sugar particles floating around in the water. Okay? The only time you break a bond is if you have some sort of chemical reaction, and we're not going to do that here. So we just dissolve it, we put it in water, it can separate. If it's... And then I didn't really talk about slamming the covalent substance, but I will talk about non-polar covalent substances. So if you think about all these other things, non-polar substance, how is that compared to a polar substance? Well, you're not going to have as many attractions. You might have a couple attractions. And of course, we still have attractions because we know that non-polar things can be a liquid, but the attractions are weaker. So these things here, they melt easier. So they melt easier or more easily. So they melt more easily. They evaporate more easily. Do they dissolve in water? It's harder to dissolve in water because we don't have charges here. So harder to dissolve in water. Okay. But if I dissolved it in something non-polar, I can dissolve this in a non-polar substance. It's like, but dissolves in non-polar substances. So non-polar things can dissolve non-polar things. Polar things can dissolve polar things. Okay. And that's where the phrase, there's a phrase that says like dissolves like, polar dissolves polar, non-polar dissolves non-polar. And so it all has to do with the charges and how it interacts with whatever you're dissolving it in. So that's covalent. Metallic things. So metallic is all metals. Okay, so metallic, all metal atoms. And I have here, this is a substance here. So I have the nucleus, and these are all electrons. So you saw the video as a sea of electrons. If I'm melting a metal, it's really, really hard to melt this metal because what are you doing to it? You're just basically giving it energy so the electrons and everything can move around. So melting, they really have very high melting points because I need to give it a lot of energy for all these electrons to get moving around. Some properties of metals, we know they conduct electricity because they have a lot of electrons. so that electrons can move around. Dissolving, do metals dissolve? Well, if I have water here, so if I have water, can it really get into anything here? And you can see there's nowhere for anything to even break up. So this sea of electrons pretty much prevents any water from getting in here. So that's why metals don't dissolve. But they are malleable. So malleable means they can be smashed with a hammer, so they can be flattened. And this sea of electron, once again, allows us to flatten it out because they're very movable. So the electrons are very movable. That's what metals are. The last kind of bonding I will talk about is something called network covalent. So we didn't talk about this in class, but network covalent is it's something like, so diamonds or sand. This is sand. These are both network covalent substances. This is kind of a strange group of substances, but typically it involves something like a silicon, which is a metalloid. So it's on the staircase, and then a non-metal, like oxygen. So let me show you what this looks like. Because of the properties of how many outer electrons there are and how they bond, it's basically a covalent bond. So we form bonds here. These are bonds. But it's all throughout, everything is connected. So diamonds have everything connected. Sand has everything connected. And because of how they're all connected, if you can imagine, if I tried melting this has an extremely high melting point. So extremely high. We're talking in several thousand degrees, because to melt this, I'd have to actually break these bonds. So if I try melting sand, we're turning it into glass, you really have to break these bonds to do that. They're really hard substances, so they're extremely hard substances. Like diamonds are extremely hard because of their structure and how everything's stuck together. So yeah, like network covalent substances, we're not going to deal with a whole lot, but just know that if there's something with a metalloid in it, like sand, or something like diamond, which is just carbon, and carbon can be connected in all directions. So if I have carbon, 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 everywhere, it's all connected. That's why diamonds are really hard. That's why diamonds have super high melting points, because in order to get them to split apart, you have to really give it a lot of energy. All right.